Here we are looking at question 69 at the end of chapter 9. And in this question, we have 5¼ grams of solid iron combined with 12.7 grams of solid elemental sulfur. This is now that I look at it, this is a synthesis reaction from elements in their standard state of iron and standard state of sulfur. The product is iron 2 sulfide. We know that that's written as FeS because iron 2 is Fe2+, and sulfide ion is automatically S2-, so they go together just with one of each ion. And the formula is a simple 1-to-1 electrolyte, FeS. Nothing much to balance. And so this is going to go together as a I was going to say equimolar of reactants, but molar coefficients of 1 and 1 respectively on the iron solid and sulfur solid. So kind of a boring reaction. I might regret doing this one because I wanted to get some more numbers, but anyway, good practice. In this question, we have 5.25 grams of one reactant and 12.7 grams of the other. We are asked to determine the theoretical yield. So think of this expression as basically saying, in theory, what is the maximum amount of product that you could produce by combining these amounts of iron and sulfur? To determine that, you have to find out which one of iron and sulfur is limiting the reaction. So which is the limiting reactant? The other reactant will therefore be in excess and not deplete, not run out. Normally when I can't do this by inspection because I have coefficients that are not 1 and 1 and 1, I would do a calculation and I'll pick another question where we can demonstrate that again. We've already done one, but we'll do another. However, in this one, it's just by inspection. So really the focus here is on the concepts of yield. So this part is simple, 1-to-1-to-1. I can just look at this to determine which reactant will run out first. And the reason why I can successfully do that is because the balanced chemical reaction tells me that I should have, have equal numbers of moles of each. Not that I should have, but that's how they go together. 1 mole and 1 mole makes 1 mole. Now, do I have equal number of moles in these masses? Well, again, when we have a mass, we convert to mole. So this number 55.85 is simply the molar mass of iron and this of sulfur. And so I'm converting mass of iron to moles of iron, mass of sulfur to moles of sulfur. So I can, in this row here, I see the numbers of moles of iron and sulfur respectively that I have reacting together. And clearly, I can see that for one, I don't have equal numbers of moles, but moreover, I have much less iron than I do sulfur. Sulfur is therefore the limiting, no, that is not true. Iron is therefore the limiting reactant because it's the smaller number and therefore it's going to run out first. And so I'm using the amount of iron to determine therefore the amount of product that I have. I will take that number of moles of iron and multiply by my conversion factor. I can see from the balanced reaction that 1 mole of iron sulfide is produced for every 1 mole of iron consumed. It's a 1-to-1 molar ratio. That converts my moles of iron to a corresponding number of moles of iron sulfide product that form. And I want to bring it to a mass because I want to calculate the mass yield. And 87.91 grams is the molar mass of iron sulfide. So don't stop the calculation there. It'll just keep going. Respect the number of sig figs should be at 3. And that's traced all the way back to your given values because everything has been multiplication and division. So we can just look at the minimum number of sig figs in the given. The answer is 8.26 grams of iron sulfide. So in theory, this is the maximum because it's determined by the depletion completely of the limiting reagent. So just tilt this down a bit more here. What else was I saying? Oh, so I've added on to this question a little bit by giving you a scenario. So that ends the question that's asked in the textbook. 8.26 grams is my theoretical yield. But let's say, for example, as I've written here, that you did this experiment and you used the same initial masses, namely 5.25 grams of iron and 12.7 grams of sulfur. That's important because otherwise we're comparing things that shouldn't be compared. So if you repeated this example, if you like to use the right word, exactly with the same starting materials and conditions and amounts, then in theory, the maximum amount of product that you would produce is 8.26. So that's your expectation. That's your theoretical yield, the maximum amount. Now you do it in the lab and, you know, some stuff escapes or what have you, it's left on the inside of the flask. But in any event, you isolate your product and weigh it. Your experimental yield, therefore, so distinguish that from the term theoretical yield, your experimental yield, because you've done the experiment, is 7.98 grams. How do you account for that? Well, it's an experiment. So some was left on the spatula, some's left on the inside, you spilled some, whatever. Okay, so that's your experimental yield, 7.98 grams. So you see how it is very, very close to your theoretical, your max, not quite. So there is a fraction here. So 7.8 is almost that full total, but not completely. So 7.98 is what fraction of that theoretical whole. So 7.8 over 8.26 will give you that fraction. I don't want a fraction yield, I want a percent. So it's kind of like a grade. You got 7.98 out of a maximum of 8.26. What is that in percent? So just multiply your fraction by 100. I don't have units down at the bottom there, 7.98 over 8.26. The units are grams over grams, so therefore they cancel. So I just have a fraction then being multiplied by 100. Excellent grade, by the way, 96.6%. And that is called your percent yield. So if you want to think of it as a relationship, as a formula, your percent yield is that fraction multiplied by 100. What's the fraction always? Well, if it's a fraction, it's less than 1, right? So you want your max on the bottom. Okay, make it make sense. So it's always going to be experimental over theoretical. Makes sense, right? Because you'd have a smaller number than 1 over the max, and times 100. So that's really it for chapter 9, isn't it? And once we get percent yield done. So chapter 9 really brings together everything that we've done except for electron configurations, but everything. So that's terrific. We still have more to do.